and we should start after all. And
Okay.
today's talk is by Anirban Basak, our nuclear physics group. And the topic of the talk is why do we do nuclear physics? First of all, I want to welcome all, and some of MSc students are also here for the talk. So thank you for joining. And I would request Anirban to start your presentation, and you can share your slides first.
Okay. Thank you, Paramesda. I would like to share my presentation.
Okay, you can share.
Okay. Is this visible?
Yeah, your screen is visible.
Okay. Okay.
You can start.
So everything is visible right now. Uh,
Yes, everything is good.
Things are moving.
Yeah, everything is good. You can
Thank you.
start.
Thank you. So I am Anirban Basak, research scholar, Department of Physics under Nuclear Physics Group, Visva-Bharati. Today I would like to give a talk on the title mentioned, why do we do nuclear physics? So if we come to the plan of today's talk, in the first portion, I will discuss about what nuclear physics is and its origin, and the later part I will discuss about the experimental nuclear physics and its applications. So the first question arises is what physics is. So physics is basically a scientific study of matter and energy and the fundamental forces that governs the interaction between the matter and energy. It is a branch of science that seeks the understanding of natural phenomena occurring in the universe and describes them using mathematical models and principles. Physics explores the fundamental principles underlying the behavior of matter and energy at various scales, like particles to vastness of cosmos. So what we can see, the physics actually explains why everything is happening. Next, we come to the purpose of physics. In one talk, to explain why what is the purpose of physics in one, it is explaining it in one talk will be very difficult. I will keep my description very small and brief. Basically, physics aims to explain the natural phenomena that we observe, and it makes prediction about how these phenomena will behave under various conditions. Uh, Physics also has a profound impact on technological advancement by understanding the principles of the physics, and also scientists and engineers have developed various technologies that have transformed our lives, like electricity, electronics, and telecommunication, etc. Physics also have its sub branches, like we all know, classical mechanics, also known as Newtonian mechanics, electromagnetism, also known as electrodynamics, thermodynamics, quantum mechanics, relativity, astrophysics and cosmology, nuclear physics and particle physics, and condensed matter physics. Also there are specialized sub branches like biophysics, geophysics, and quantum optics. Now I will focus my talk on nuclear physics. In nuclear physics, the study is conducted to study the nuclear structure, nuclear reaction, radioactive decay, nuclear fission, nuclear fusion, and nuclear astrophysics. Nuclear physics actually investigates the internal structure of atomic nuclei. It examines the arrangement of proton and neutron, and their distribution, their energy levels, their interaction between the nucleons. The understanding of the nuclear structure is crucial as it explains the nuclear phenomena and its property. Whereas the nuclear reaction that involves the process where the atomic nuclei interacts with other nuclei, or proton or neutron beams. This reaction can be induced by bombarding that I have mentioned. This reaction can be induced by bombarding nuclei with other particles. The nuclear physics studies the characteristics of and the results of the outcomes of these reactions, including the product nuclei and the amount of energy that released in this reaction. Also, we observe the radioactive decay, uh, which is a process in which unstable nuclei undergo spontaneous transformation by emitting radiations like alpha, beta, and gamma rays. The nuclear physics investigate these decay rates of alpha, beta, gamma radiation and the nuclei and decay modes and their underlying mechanism involving these radioactive decays. The next part comes is nuclear fission, where the heavy atomic nuclei splits into two or more smaller fragments accompanied by release of significant amount of energy. This process is the basis of nuclear power and nuclear weapons. Uh, nuclear physics studies the condition and the dynamics and the consequences of nuclear fission reactions. Uh, Similarly, there is also a process called nuclear fusion in which the light atomic nuclei uh, fuses together to form a heavier nucleus, and in this process a vast amount of energy is released. It is the fundamental process that powers stars like our sun. Nuclear physics also explores the condition required the fusion reactions, fusion cross sections, and it challenges us for achieving controlled fusion on Earth. In the part of nuclear astrophysics, we focus on the nuclear reaction and the process that happens in stellar evolution, nuclear synthesis, and the energy of the production in stars. It investigates the behavior of matter at extreme temperature and high densities, such as such found. It is found nuclear which is found in the cores of the star during stellar explosions. There are also other aspects of nuclear physics which we will mention later in this talk. Now, if we come to the origin of the nuclear physics, it all started in the late 19th century when the scientists Henry Becquerel and Marie Curie and Pierre Curie made an important discovery related to the radioactivity. What they observed is some material emits radiation, and Marie Curie was the first person who coined the term radioactivity. Later, J. Thomson proposed the palm pudding model in 1904, suggesting that atom is consist of positively charged pudding with negatively charged electron are embedded within it. As we can see in the picture, this model laid a groundwork for understanding the structure of atom. In 1911, Rutherford did his gold foil experiment by bombarding alpha particles into a thin gold foil, and he discovered that most of the alpha particle passes through it. As a result, he concluded his conclusion by a new model called Rutherford's nuclear model, in which he concluded that the atom has a dense positively charged nucleus at its center. In 1913, Niels Bohr expanded Rutherford's model by introducing the concept of quantization of energy within the atom. His model, known as Bohr's atomic model, which explains the stability of atom and the emission and absorption of radiation by electron transition between the energy levels. Later, in 1932, discovery of neutron by James Chadwick provided a better understanding of the composition of atomic nuclei. Basically, we can consider the discovery of neutron as the proper origin of nuclear physics. Also, in early 2000th century, there observed many nuclear reaction like Enrico Fermi and Otto Hahn made a significant discovery by performing experiment on uranium 235, where they observed the fission of the nucleus. This early development laid a foundation field for the nuclear physics. If we talk about nuclear physics and don't talk about Madame Curie, then it will be unfair, because in because she was the first person who coined the term radioactivity. Marie Curie was born in 1867 in Poland. Uh, in 19th century, Marie Curie began her investigation and the phenomena regarding radioactivity. In 1988, she and her husband discovered two new radioactive elements, polonium and radium. The polonium element was found after her native land, Poland. The discovery of known element expanded by this discovery, and Marie Curie also developed innovative technique to isolate and study the radioactive substance. She developed methods to extract pure radium and measure the radioactive property with very accurately. Her work involved handling highly radioactive material. Its radioactive material His work involved handling highly radioactive materials. She also termed the word radioactivity. Marie Curie developed the sensitive instrument which is called electrometer, which allowed for precise measurements of radioactivity. This instrument played a crucial role to study the radiation and its property. She also developed a theory of radioactivity with her husband Pierre Curie and the physicist Henri Becquerel. Uh, After discovery of this theory, she and her husband and Henri Curie received Nobel Prize in 1903, and she was the first woman who received the Nobel Prize. It must be mentioned that in 1911, Marie Curie received her second Nobel Prize, this time on chemistry, in recognition of her discovery of radium and polonium. Her groundbreaking research on radioactivity actually laid the foundation of modern nuclear physics. Now we have seen that the nuclei, the radioactive nuclei emits different kind of radioactive particles like alpha particle, beta particle, and also some rays called gamma rays. So we need some detectors like particle detectors and gamma ray detectors, which can detect the particle and its energy. Um, in the case of particle detector, the first name comes our mind is GM counter or Geiger-Müller counter, that detects the ionizing radiation such as alpha particle and beta particle, and also it detects gamma particle, but with a low efficiency. It works by using a gas filled tube that ionizes when a particle passes through it, and it produces the electric signal that can be measured and counted, and that counts the number of particles passed through the chamber in a certain time. There is also scintillation detector that uses a material called scintillator, which emit flashes of light, which is called scintillation, when they are struck by charged particle or high energetic photons. These flashes of light are converted into electrical signals and can be used to determine the energy and the type of particles. PMT or photomultiplier tubes are often used in the conjunction of scintillator and it can be used to amplify the faint light signal produced by the scintillator. PMT consists of photocathode, electric multiplier stage, and an anode, which generates the electrical signal proportional to the intensity of light. As we can see that it depends the this electrical strength of the electrical signal depends on the intensity of the light that emitted by the scintillator, and the photocathode here is used to amplify the intensity of the electric signal. There are also some detectors are called time projection chamber or TPCs, which measure the position and momentum of charged particle in 3 dimensions. They actually consist of the gas filled chamber with a drift region. I will not go into details for TPCs because they are not used drastically. Uh, the Cherenkov detectors can detect the Cherenkov radiation. Cherenkov radiation is emitted when the charged particle moves through a medium with a faster than the speed of light. The schematic diagram of Cherenkov detector is described in the right side of the screen. By measuring the intensity and the direction of the Cherenkov radiation, the information about the particle can be obtained. In this case, I have mentioned very few number of particle detectors, but we will focus our talk on gamma detectors. So scintillator detector, we can see scintillator detector is a very efficient gamma detector. Scintillator detectors such as sodium iodide crystal doped with thallium ions or organic scintillator are commonly used for gamma ray detection, as it has very good efficiency. When a gamma ray interacts with the scintillator material, it produces, as I mentioned, it produces a flash of light. A photomultiplier tube with attached with it or a silicon photomultiplier are used to convert the scintillating light into electrical signal that can be measured and analyzed. Germanium detector or highly purified germanium detector, which is shortly called HPG detectors, offer excellent energy and resolution and well suited for gamma ray spectroscopy. Germanium detectors are made from specially grown germanium crystal that operate at very low temperature. The low temperature is made by liquid nitrogen or other cooling method like liquid helium. When gamma ray interacts with the germanium crystal, it creates actually electron-hole pair, and the resulting charge is measured to determine the energy of the gamma ray. Semiconductor detector such as cadmium zinc telluride or commonly known as CZT or silicon detectors are used for gamma ray detection. Similarly, HPG detector, semiconductor detector, operates measuring the charge produced when the gamma ray interacts with the semiconducting material. They offers very good resolution and can be more compact and portable than HPG detectors. There are also Compton scattering detector, which uses the effect of Compton scattering, which occurs when the gamma ray scattered by an electron. By measuring the energy and the direction of the scattered gamma ray, we can get information about the incidented gamma ray. Compton cameras, which are very portable, and Compton camera employed to detect Compton scattering detectors are actually the Compton cameras that are used in medical imaging and gamma ray astronomy. The sodium iodide well detector. A description and the physical description of sodium iodide well detector is described in the right side. Sodium iodide detector is consists of cylindrical sodium iodide crystal with a well or hole in the center, as we can see in this picture. These are primarily used for very high energy gamma ray, and it has very good efficiency for detecting photons. The well in the detector helps to optimize the sensitivity of the various gamma ray from various direction. There are also plastic scintillator detector, which are very portable than also semiconductor detector and HPG detectors. And now we come to the gamma spectroscopy. and using this detector, we perform experiment by arranging an experimental setup and detecting gamma ray. Then we perform energy calibration and the spectrum acquisition, and then we identify the peak, and ultimately we draw a level scheme like this with various decay path and transition. So in our experiment setup, what we do is play a target material is placed in a certain position, and it is bombarded with particles like proton, neutron, and it can be other nuclei to induce nuclear reaction. And also what we can do in our MSc lab is a radioactive sample is placed near the detector, which emits alpha beta rays, but which are the isotopes which have very small lifetime cannot be the life cannot be measured in like this way. So we need to produce a proper experimental setups, and I will later discuss the experimental setups in India and abroad. I will leave this part for now. So what we have observed that the in experiment, by bombarding some particle on the target nuclei, we get residue nuclei. After the residue nuclei comes to the ground state by emitting gamma rays. So we need to detect those gamma rays. The emitted gamma rays from the nuclear reaction are detected by the detectors, gamma ray detectors I have mentioned in the previous slide. This detector, what the detectors do, as I mentioned, these detectors converts the energy of gamma rays into electrical signals that are processed and analyzed by physicists. So what physicists do is firstly they calibrate the energy spectrum by gamma ray spectroscopy system. Using known gamma ray, they calibrate the energy spectrum, which is nothing but relationship between the energy of the gamma rays and the electrical signal. This is a example of how the gamma ray spectrum looks. Mm, the calibration process is very much important, very much as it as it helps to calibrate the system and to determine new gamma rays as we go further. Now the spectrum acquisition. The electrical signals from the gamma ray detector are processed and converted into the spectrum, which are called gamma ray spectrum. The gamma ray spectrum actually represents the number of gamma rays detected at different energy levels. Now the peaks are identified in the gamma ray spectrum, and we get a level scheme like this. The most required information is to obtain the level scheme of the residue nucleus and the assignment of spin parity of the excited state. Now I will come to the different facility where the experiments are done in India. Bhabha Atomic Research Center, which is known as BARC, located at Mumbai. BARC is an Indian premier nuclear institute. It houses several nuclear facilities for nuclear research and also material science research, radiation biology, and medicinal research. It also homes Indira Gandhi Center of Atomic Research Center, which is known as IGCAR, which focuses on the fast accelerator. Now we come to VECC, which is Variable Electron Cyclotron Center, located at Kolkata, is a national research facility that operates a cyclotron, which is called K130, and there are also a semiconducting cyclotron, which is an R&D stage that provides various beams for nuclear research. There's also Inter University Accelerator Center, IUSC, which is situated at New Delhi. It operates several particle accelerator using a 15 UD electron accelerator and supported research in nuclear physics, material science, radiation biology, and also other subpart of the physics. Uh, RRCAT, the Raja Raman Center of Advanced Technology, also focuses on advanced study in nuclear physics, and it operates a synchrotron radiation facility called naming INDUS-2, which provided intense X-ray and ultraviolet beams for material research, spectroscopy, and imaging techniques. Though it is not used in case of nuclear physics, but I have mentioned this because it is a very much it is a very good synchrotron which uses the beam like X-ray and ultraviolet beams. There are also nuclear physics laboratory like SINP in Kolkata. There are also TIFI Mumbai, and there are various groups in Delhi University, Visva-Bharati University, IIT Rourkela, and etc. The university basically conduct research in nuclear structure, nuclear reaction, and nuclear astrophysics related areas. There are also numerous nuclear accelerators around the world, ranging from small scale accelerators which are used for research purposes and large scale accelerator which are used for particle physics experiment. Here I have mentioned very few number of accelerator centers like LHC, which is Large Hadron Collider located at Switzerland. LHC is the world's largest and most powerful particle accelerator, which consists 27-kilometer ring consisting made of superconducting magnet that are used to collide proton and heavy ions at very high energies. These are generally used for particle experiment studies. There are also Fermilab, which is situated at United States, also used for particle physics studies, and it operates many accelerators like Tevatron, which uses the world's highest energy particle collider, until LHC surpasses it at 2009. There are also SLSC National Accelerator Laboratory in US, KEK in Japan, GSI Helmholtz Center for Heavy Ion Research located at Germany, JINR, the Joint Institute of National Research located in Dubna, Russia, and also there are R&D facility ESS, European Spallation Source, which will produce next generation accelerator and being constructed in Sweden. Now I come to the application part of the experimental nuclear physics. I have mentioned the gamma ray spectroscopy. Using this gamma ray spectroscopy, what we get is actually a level scheme which looks like this. A zoomed version of the level scheme is mentioned at the right side, where the arrow is mentioned the gamma ray transition, and I have mentioned the reduced transition probability, or you can think of this is a probability of the probability for this possible transition in the Wiscop unit by the arrows. So actually, two-state mixing models describes that these energy level what we see in the level scheme are basically unperturbed energy level, and we do not get any idea of the unperturbed states and how this perturbation occur. Consider this 2 0 plus state. These 2 0 plus states are basically perturbed energy level. Because they have an interacting potential between them, which um, which provided the perturbation between them. So if we can see that, suppose we consider two unperturbed level which are denoted with energy H1 and H2, which have and the wave function phi1 and phi2, and the interacting potential between them is V12, then they after perturbation they produces two new energy perturbed energy level which have energy E1 and E2. By using eigenvalue equation and reproducing Hamiltonian in the matrix form, we can obtain the energy eigenvalue in terms of the unperturbed energies and the interacting potential. So as we can see that if we know the energy of the unperturbed state and the interacting potential, we can determine the energy value of the perturbed state. Can we think it as a vice versa? Like if we know the energy of the perturbed state, we can determine the interacting potential between them. It is done by two-state mixing model, where we consider the energy of the perturbed levels which are obtained from gamma spectroscopy. Like this zero state is a ground state for cadmium 112, and this zero state is the second excited state, which has energy 1244 in keV unit. These two are the perturbed energy levels. If we consider the wave function of the first zero state as the linear combination of of a ground state and a excited state with the coefficient a and small b, we can represent the wave function of two perturbed state as 01 and 02. Similarly, if we consider these two plus states which are labeled in green, they mixes and produces the mixing. Hence we can write their wave function as a function of as a superposition of two states, which consist of 2G, that is ground state of the corresponding 2 spin state, and excited state of the corresponding 2E state, 2 plus state, and they're combined with the coefficient capital A and capital B. Here we introduce operator BE2, which is nothing but I have previously mentioned, it is the reduced transition probability, which can be measured experimentally. And here we actually introduce new factor M, which is defined as this equation. So and we also introduce the new matrix element, which is defined by Mg and Me. From this we can determine the 4 value by operating these wave function together, and these operator together we can determine these 4 value, and we can match them with the experimental result. So if we operate this on Me2 without knowing their internal structure, and that is, we assume that we don't know the internal structure of this wave function, and these ground state are linked with each other by Me2 operation, and ground state and excited state are not linked with each other. If we assume these assumptions, then we can find the interacting potential corresponding the zeroth state is 422 keV, and the second state, then the 2 plus state is 387 keV. Now if we see that there is a square term in M, so if we make root over this, there will become plus and minus. For our convention, we consider M0 and M3 to be positive as their interband transition. But in the case of M2, we can consider both, that is plus and minus, as they perform destructive interference. So if we take the M2 positive, we get this result, that is for j equal to 0 we get 422 keV, and for j equal to 2 we get 387 keV. If we take the M2 as negative, we get this result, 297 keV and 367 keV. So from these calculations, we can determine the mixing potential of different states, and from this we can actually see how the unperturbed level will look like. So ultimately we can determine the mixing potentials, and we can deeply investigate the unperturbed level scheme of any nuclei. And there is one problem that arises. If you can see that we are taking only low spin levels, because here the BE2 values are very high, and as well, so we get the ME2 values also calculatable. But if we go in the higher state, we will see that the BE2 values for this transition will get very low. As a result, the Me2 value will be very low, or sometimes it is unknown. That means the experimentally they are not observed. So we cannot calculate those mixing potential till now. So I would like to conclude my talk by this summary, that nuclear physics still holds a great potential for nuclear research. With vast and complex subject matter, with a thorough understanding of the theoretical model, we can effectively explain natural phenomena in a precise and accurate manner. This knowledge allows us to provide comprehensive explanation that is both professional and easily understandable. There are also numerous emerging opportunities in India, such as INGA 2.0. INGA stands for Indian National Gamma Array. It is actually a campaign which is held by all the nuclear facilities to differ for different nuclear experiments regarding nuclear structure, regarding nuclear mechanisms and everything. And there are also ANUDIM that stands for Applied Nuclear Physics, using rare isotope beams, and as well as in abroad like FAIR in GSI, which is in development. And ultimately, I would like to thank everyone for joining in. Thank you.
And everyone, thank you for your talk. And you described the other experiments also very well, and other opportunities inside India and outside India also. And anyone have any question?
Hello.
Yes.
Am I
You are
audible?
audible.
Yes. Yes.
Yeah. So I have a question.
Yes.
In slide number 9, you have told that
Okay.
told about the energy calibration.
Okay. Wait
You
one
told
second.
that it is needed to yeah. You can open the
Yeah.
slide number 9.
Yes. That's number
Yeah.
9.
So you told about the energy calibration, right?
Hmm.
So it is needed to convert the particle count to electrical signal, right?
Yes.
Okay. So how frequent you have to calibrate the instrument? Is it monthly,
Uh,
yearly, or
no. Actually,
fixed?
what is done, when the experiment is performed, the data are taken. Then we get the data, and using the data, we have to calibrate it first. And each experimental setup has its own efficiency. So if your efficiency calibration and their efficiency calibration match, then you can progress. Otherwise, it won't. So there's a very much difficulty in energy calibration process. Different
Okay.
experimental setup had different calibration techniques and different efficiency.
Okay, Anirban, thank you.
Okay, anyone else? Only, but I need to add something that you have
Okay.
told about the RR-CAT synchrotron detectors,
Huh.
synchrotron beam generators.
Okay.
They are mostly used for X-ray,
X-ray.
X-ray, XRD, or you can say
XRD. Yes.
X-ray
Yes.
diffraction
XRD. Yes.
for any
Yes.
kind
Yes.
of materials.
Yes.
We kind of use these kind of things
Huh.
for very thin films. If you want to know the structure of the material, so
Okay.
we use this RRCAT facility, their synchrotron facility,
Hmm.
and they produce very high energy beams and very stable beams. It's really rare to get a stable XRD beam with that high energy. So
Okay.
RRCAT provides that facility with their synchrotron for us, for the material scientists.
Yes. Yes.
Okay. And anyone else wanna ask something? The questions can be random. Okay. You don't need to
Yes.
ask him about the nuclear physics only. Okay. Sumanda, you can speak up. You can ask anything.
Okay, am I audible?
Yeah,
Yes.
Sumanda. Yes.
Yeah, so as nobody is asking questions, I had a couple of questions. So,
Okay.
Anirban, first of all, it was a very nice talk. So, in the gamma ray spectroscopy, you are looking at some peaks, like you're
Okay.
looking for some peaks for gamma ray. So,
Okay.
what are the chances or what are the possible sources for false alarm, like false
Um,
detections?
there's a false
How
alarm.
often do you get?
How far do we get? Detecting a actual peak is very important in the fast process. Okay, so there are like background noises and Compton scattered peak. So you need to detect which peaks you need to choose at first your detection. That actually comes from your experience and knowledge of the detectors and as well as the materials you are going with.
Okay, my second question would be, let's say for any the detector in IUAC. So
Okay.
their probe, how many detectors are there?
There
Uh,
are like 14
so
usable
they
detectors.
so they
14
are not
per
covering the
detector.
okay. So they are
They,
not covering the entire.
no, no, no,
Yeah.
no, no, no 4 pi, no 4 pi, no
So
4 pi.
how do they compensate for, like, do they
They have
prepare
certain
the result?
angles. They have certain angles. You can place it like
Okay.
178 angles, like 0 degree angles, 90-degree angles. According to your specifications, they will set the angles. So you have to request them that I want to set this angle and the angle. Actually what happens, they choose the angles and they say I have set the angles and you take the readings for these angles. So
Okay. So
like
the
that,
it is entirely angle dependent.
angle dependent. Yes, yes, yes.
So, and my third question and yeah, last question would be, I have no idea about the single detectors. What they are, like current detectors, do they still have gas or just
No, they are scintillator detectors are not the gas detectors. They are actually sodium iodide detectors. They are crystal detectors. Oh, they are not gas.
the scintillator detectors, do they still contain gas?
Uh, they contain gas for quenching.
Uh, okay. Hello.
Yes. Hello. Am I audible?
Yeah, you are audible. What do you mean by quenching here?
Anyone?
Okay. What is quenching means? So as you can see that in what happens, the GM
Am I
count
audible?
is basically a gas filled detectors. Okay. So what happens when a beam beam basically consists of number of particles. When a particle enters, that breaks the gas ion into a cation and anion, and there is a anode in the middle, and cathode. So the positive cation goes to the negative part, and negative ion goes to the positive part, and we get a electric pulse. So if the continuous emission, continuous incidence of the particles will cause a drastic what do you say, damage in the field gas. So what we cannot do is that change the gas in every time when the experiment is done. So what we do is put a quenching agent. Basically, in this GM counter case, we put ethyl alcohol in certain percentage. As a quenching agent, which provides the extra electron when the electron is say removed from the gas atoms, and they get the extra electron from the ethyl alcohol vapor, and they produce again the gas molecule. So the longevity of the counter becomes very high. Otherwise, it will be very low, and we have to change the gas many times.
Okay, I get that. And I don't think the scintillators are using gas
Oh,
inside the chamber. There should be a vacuum, good vacuum for get
okay.
get the scintillator. You know better. I think there is a vacuum inside the photomultiplier tube.
Yeah. A scintillator is basically like that. No, scintillator is this, and PMT is cathode. Like this is a PMT.
Okay,
This part is a PMT, and this part is a scintillator.
okay. Mondas, we cannot hear you the last part.
Okay, it was done actually. I got all the answers. That
Okay, thank you.
thanks, Anirban.
Okay, thank you, Anirban. If anyone else don't have any question, we will conclude the session. And thank you, Anirban. Thank you, everyone
Thank you.
else, for joining. And we will meet again next month.
Thank you.
Okay.